Hello friends, welcome back to all about structural analysis and design. So in this lecture, we will see how to analyze a indeterminate beam with the help of slope deflection method. We have also seen previously there were 3 videos about slope deflection method. So this problem is unique because in this problem, the support is sinking. So previous 3 problems didn't had any sinking of supports, but in this problem I have considered a support is sinking by certain amount. So let's see the problem statement. So it says calculate the moments for the given beam if support B sinks by 2.5 mm and for all members I is equals to 3.5 into 10 raised to 7 mm raised to 4 and E is equals to 200 kilonewton per mm square. So this is the speciality of this beam because in the previous 3 videos we have seen where EI was constant or I value was varying. There was no numerical value of E and I. Whereas in this problem there is a numerical value for I as well as E and also the support B. So this support is sinking by how much magnitude? 2.5 mm. So all these things will be considered in this problem and it will be explained in step by step. So if you want to go back to the previous videos, so I will be sharing the link in the description box. So all the 3 videos are accessible in the description box through the given link. So let's start with today's video. So first step is to find out fixed end moments. Fixed end moments. So there are 2 types of load considered here. One is UDL and another is point load at the center. So for UDL, the fixed end moment formula is WL square by 12. So we have designated fixed end moment as MFAB. So each span by span you have to find out. So for AB there will be 2 moments. One is MFAB and another is MFBA. So A to B and B to A. So MFAB will be considered as negative because it will be rotating anti-clockwise and MFBA will be considered positive because it will rotate clockwise. So all these things are explained in the previous videos and also there is a playlist of slope deflection method. Please go through it so that you will get clear idea about what we are speaking in this problem. So MFAB will be anti-clockwise like this. So therefore it is a negative sign and the fixed end moment for UDL is WL square by 12. So W in this case is 40, length is 3 meters, so 3 square divided by 12. So you will get minus 30 kilonewton meter. So similarly MFBA, it will be positive because it will rotate here clockwise. So WL square by 12. So 40 into 3 square divided by 12. So it is 30 kilonewton meter. So similarly now you have to come to span BC and there will be again 2 fixed end moments, that is MFBC and MFCB. So BC is anti-clockwise, CB is clockwise. So again same pattern we have to follow for the sign convention, anti-clockwise negative, clockwise positive. So MFBC minus, but here the fixed end moment for point load at the center is WL by 8. Minus sign for anti-clockwise. So W is 100, length is 2 meters divided by 8. So it will give minus 25 kilonewton meter. So similarly MFCB, positive WL by 8. So 100 into 2 divided by 8 you will get 25 kilonewton meter. So similarly for span CD, MFCD and MFDC you have to calculate. This is UDL, so same WL square by 12 will be applicable. So MFCD minus WL square by 12. Here the W is 50. In this case it was 40. Here in this case it is 50 kilonewton per meter. So minus 50 into length is again 3 square divided by 12. So you will get minus 37.5 kilonewton meter and MFDC is positive because it is clockwise. So WL square by 12. So 50 into 3 square divided by 12. So positive 37.5 kilonewton meter. So this is very important step when you are solving a indeterminate structure with the help of slope deflection method or slope deflection equations to calculate fixed end moment. So if you go wrong here, so all the values in the subsequent steps will be wrong. So carefully understand the loading pattern, and with respect to the loading pattern, you have to write the formulas for fixed end moments. So this is your first step. Now second step is to get the value of EI. So in this case, E and I values are given, but if you see carefully, the units are different. So our beam measurements all are in meters. So here the I value is in mm and also E is in mm. So kilonewton is there, so we will not disturb this kilonewton. So from mm to meter we have to convert it. So step by step we will consider. So E value we will convert first. So it is given 200 kilonewton per mm square. So we are not changing 200 this one kilonewton, so we'll keep it as it is. So per means it is divided by. So from mm to meter, if you want to consider, you have to divide it by 1000. So 1 divided by 1000 square, because it is mm square. So if you do this, the E value will come 200 into 10 raised to 6 kilonewton per meter square. So this is your E value. And next, similarly, we have to convert I value. So I value given is 3.5 into 10 raised to 7 mm raised to 4. So I is equals to 3.5 into 10 raised to 7. So same way again, 1 divided by 1000 raised to 4. So I value comes out to be around 3.5 into 10 raised to minus 5 meter raised to 4. So this will be your I value. Now we want EI combined value. So EI is equals to, so E is 200 into 10 raised to 6 and I value is 3.5 into 10 raised to minus 5. So once you multiply this EI value, you will get 7000 kilonewton meter square. So this will be your EI value, which we have converted from millimeter to meter. So this will be your second step in this particular problem. Now once you convert the EI value, then we have to go for slope deflection equations. Slope deflection equations. So in detail we have seen the slope deflection equations in the previous videos. So directly I'll write down. So we want the moments. So support moment means, or calculate the moment means, so there will be a total of 6 moments: MAB, MBA, MBC, MCB, MCD, MDC. So whatever you have calculated fixed end moment 6 times, so same way you have to calculate the moments 6 times. So therefore there will be a slope deflection equation for the respective moments. So MAB is equals to MFAB. So fixed end moments you have to take for that particular span and that particular designation, plus 2 EI by L, 2 times theta A plus theta B minus 3 delta by L. So before moving again in this particular problem, we shall write down here, as you can see in the beam, end A and end D is fixed. So therefore there will not be any theta, or there will not be any rotation at A and D possible. So only possible rotations are at the point B and at the point C. So theta A and theta D will be 0 because the ends are fixed. So we will write down here as A and D are fixed. Therefore theta A and theta D is equals to 0. And also delta comes into picture. Delta is nothing but 0.0025 meter. So actually the given sink is 2.5 mm. So if you convert 2.5 mm, so it will comes out to be 0.0025 meter. So here delta we have to substitute 0.0025. So there is a sign convention, so which we will see here how to take the sign conventions for the delta. So now I will show you the substitutions. So MFAB is minus 30 plus 2 EI value we have calculated, and that is 7000. Length for the span AB is 3 meters. So theta A is 0. So theta B minus 3 times delta. Delta what to take? So we will see here. So actually if you see, this is your end A and this is your support B. Okay, so this is A and B, and now the B is sinking by some amount, and that amount is 0.0025 meter. Per sign convention, if right side support is going down compared to left side support, so this will be your left hand side support and this will be your right hand side support. Carefully understand, the delta is positive if right hand side support is down compared to left hand side support. So here this right hand side support is going down by 0.0025 meters compared to left hand side. So therefore the delta will be positive. Okay, so here I can write down 0.0025 divided by span, bracket complete. So this is positive delta if right hand side support is going down compared to left hand side support, then the delta is positive. So positive delta has been substituted. Now just the simplification. So once you simplify it, so minus 30 will remain here as it is. So plus 2 into 7000 divided by 3 into theta B if you do, so 4666.66 theta B, and this quantity 2 into 7000 divided by 3 into minus 3 into 0.0025 divided by 3, if you do, it comes out to be 11.66. So therefore the simplified version will be MAB is equals to minus 41.66. so this we have to simplify, plus 4666.66 theta B. So this will be your equation number 1. So like this way, for BA, BC, all those moments equation we have to calculate. So now the next equation, MBA, MFBA plus 2 EI by L. Now 1 time theta A plus 2 theta B minus 3 delta by L. So this will be the slope deflection equation for this moment BA. So now MFBA is 30 plus 2 EI value is 7000, span is 3, so theta A is 0 because end A is fixed, so 2 times theta B minus 3 into, now the sign convention remains same for the span AB, so there is no change, so positive 0.0025 meter you have to substitute here, and now you can simplify. So MBA equation will be 18 point, so once again complete I'll write down, so 30 plus this quantity into 2 times theta B will give you 9333.33 theta B, and this quantity will be in minus this into this, so it is 11.66. so MBA equation you will get 18.34 plus 9333.33 theta B. So this will be your equation number 2. Now you have to take for span BC. So MBC is equals to MFBC plus 2 EI by L, 2 theta B plus theta C minus 3 delta by L. So now we have to be careful again for the span BC because the sign convention changes here. So the sign convention, what it says, if delta is positive if right hand side support is going compared to left hand side support. So in previous case the delta was positive. Now we will see the next case. So now support B is this for the span BC, and this is support C, and support B, as we know, it is sinking by 2.5 mm. Okay, so that is 0.0025 meter. So now this time it becomes here LHS and this is RHS. Now as per sign convention, the delta is negative when left hand side support goes down compared to right hand side support. So if you see here, in the previous span, left hand side support was at the top, right hand side support was at the bottom, therefore delta was positive. Here left hand side support is going down compared to right hand side support, so therefore delta will be negative here. So this will be minus 0.0025 meter. I hope you understand. So once again I'll repeat, if left hand side support is going down compared to right hand side support, then the delta becomes negative. So now we have to substitute here MFBC is minus 25 plus 2 into 7000 divided by, the span is 2 meters, 2 theta B, theta C also will be there because both are simply supported, minus 3, and here you have to substitute minus 0.0025 divided by 2. I hope you have understood how to substitute delta. So once you simplify, so this will remain minus 25. So this into this, you will get 14,000 theta B plus 7,000 theta C. This minus into minus plus, so this will be plus 26.25. So MBC, if you simplify, you will get 1.25 plus 14,000 theta B plus 7,000 theta C. So this will be your equation number 3. So similar way, now MFCB plus 2 EI by L 2 theta C plus theta B minus 3 delta by L. MFCB is 25, 2 7,000 into 2 into 7,000 divided by 2. So now 2 times theta C plus theta B minus 3 into minus 0.0025 divided by 2. So MCB is 25 plus 14,000 theta C plus 7,000 theta B plus 26.25. So therefore MCB is equals to 51.25 plus 7,000 theta B plus 14,000 theta C. So I have rearranged the term, first theta B, second theta C I have written. So this will be your equation number 4. MCD, okay, here delta will not come because B was sinking and B was corresponding to span AB and BC. So CD span is irrespective of the support B. So therefore the supports are not sinking, so here delta will be 0. So the moment slope deflection equation is MFCD plus 2 EI by L 2 theta C plus theta D minus 3 delta by L. So D is fixed, so theta D will be 0, delta is 0 in the case of span CD, so these two terms will be 0. So substitute MFCD is minus 37.5 plus 2 times 7,000, length is 3 meters in this case. So here the only remaining is 2 theta C. So MCD equation will be minus 37.5 plus 9,333.33 theta C. So this will be equation number 5. So similarly, the last moment equation MDC. So MFDC plus 2 EI by L 2 theta D plus theta C minus 3 delta by L. So these terms, two terms will be 0. So therefore MFDC is 37.5 plus 2 times 7000 divided by 3 into theta c. So MDC equation will be 37.5 plus 4666.66 theta c. So this will be equation number 6. So now you have to apply equilibrium conditions. At which point, so if B joint has to be stable or B support has to be stable, then MBA plus MBC is equals to 0. Then moment at C, MCB and MC plus MCD should be equal to 0. Okay, so to remain stable B and C, these are the two equilibrium conditions. So we have to make use of these two equilibrium conditions to get the values of theta B and theta C. Now using equilibrium conditions, at B, MBA plus MBC is equals to 0. MBA is nothing but your equation number 2. So this equation plus MBC equation, for that MBC is the third equation. So second and third equation you have to add and equate it to 0. 23,333.33 theta B plus 7000 theta C is equals to minus 19.59. So this will be your equation number 7. So similarly, equilibrium equation at C is MCB plus MCD is equals to 0. Once you rearrange all the terms, you will get the equation as 7000 theta B plus 23,333.33 theta C is equals to minus 13.75, and this will be equation number 8. So once you get the equation 7 and 8, you will be solving it. So solving 7 and 8. So once you solve this in your calculators, you will get the theta B value, and that comes out to be minus 7.283 into 10 raised to minus 4, and theta C will be minus 3.7078 into 10 raised to minus 4. So now you have got the rotations at point or at support B and C. So now you have to substitute these two values in equations 1 to 6. So the equations 1 to 6 which all you have calculated or which all you have arrived, that in that equations you have to substitute these theta B and theta C values and get the final moments. So once you substitute, you will get the values, and that values will be MAB is equals to minus 45.05 kilonewton meter, MBA will be 11.54 kilonewton meter, MBC will be minus 11.54 kilonewton meter, MCB will be 40.96 kilonewton meter, MCD will be minus 40.96 kilonewton meter, and MDC will be 35.76 kilonewton meter. So this is how you have to calculate the end moments. And once you do this, the bending moment you have to draw, and the bending moment will be pattern like this. So this, whatever the black portion you can see or black shading you can see, it is for the loading, and whatever you see the red marks is your end moments. So this is WL square by 8, so you will get 45 kilonewton meter for the loading of for the loading of 40 kilonewton for 3 meter span. So it will be 45. So 100, that is WL by 4. So point load at the center. So will be 50 kilonewton meter, and for this 50 kilonewton per meter, it will be 56.25 kilonewton meter will be the loading bending moment diagram. Now what we have to do is, whatever the end moments you got, you have to overlap and get the points or mark the points in such a way that all should be connected, and that will be your net bending moment diagram. So this is how your bending moment diagram should be drawn. So I hope this video was helpful for you. So we have learnt how to incorporate sink in the given problem, and also we have converted E and I values and all values were substituted, and also we have seen the sign conventions when the sink is given. So with the help of those things, we have calculated their moments and arrived at the final bending moment diagram. So I hope this video will help you to solve these kind of problems. If you have liked this video, please like it, share it, and don't forget to subscribe all about structural analysis and design. Thank you, friends.